we have been looking at this particular situation where the particle is sitting in the well and the potential is infinitely high, right? So this is essentially the case we are dealing with here, okay? So for example, here the particle is inside the well, and as we kind of discussed, for several weeks, we are essentially looking at this particle, but when we are lowering the dimensions of the object, the wave phenomena becomes very apparent, right? Obvious. Okay. So in the sense that we are essentially looking at particle wave duality, and in quantum world, what our interest is mainly a very small scale object like electrons or atoms, that scale. Okay. So when you are looking at this kind of particle, obviously it's going to have wave characteristic, and then we are trying to find out, the solution for this wave behavior. Okay, so in the sense, since this one is a wave, we cannot really find out where the particle position is exactly. Okay, so this is why we are trying to find out the average value of position and average value of momentum. Okay, so that is essentially kind of our focus. And then first of all, you have to get the solution for Schrödinger equation. And then if you solve the Schrödinger equation, it's going to give you the wave function, right? Wave function psi here. But once you get psi, you can get probability density function. And then that probability density function is going to tell you the probability distribution of the position for this particle or wave, right? So with that, we are looking at the average value of position. Okay, so with this lengthy process, you are using position operator, and then we finally got this value, right? It's essentially constant value. Here the value is a d over 2. Okay, so let me just kind of describe a little bit more about implication here. Okay, so wave function. Okay, this is wave function that we got by solving Schrödinger equation, right? This is a sine n pi over dx. And remember, this n is just integer, right? N goes from 1, and then you can take only integer values. So for that one, let me just kind of describe this wave function one more time here. So we are really looking at when x is 0, and then when x is d, basically these are the walls, right? And then outside of the walls, the wave function is 0, right? Wave function is 0 outside of the wall. But inside this cavity, inside this well, we can describe wave function. But obviously it depends on the shape, depends on n, right? So for example, when n is 1, it looks like this. And then when n is 2, this is essentially when n is 2. And then if n is 3, it looks like that, right? We are essentially kind of drawing multiples of a standing wave, right? This is when n is 1, this is the longest wavelength, n is 2, n is 3, okay? So then let's look at the probability density function, okay? So for example, here psi n star psi n, this gives us probability density function. And then if we draw that, so again, when x is 0, and then when x is d, we can easily get this probability density function because we already know what this psi n is, right? So let's kind of draw that. So what that means is that when n is 1, this n is 1, okay? So we are essentially kind of doubling up, right? Because we have psi n, this is a real number, and then psi n, you're essentially kind of multiplying. And then if n is 2, this is positive value, and then positive value, this positive, but this one is negative value, right? This part, negative value multiplied by negative, it becomes positive. Okay? So in the sense, this will be essentially look something like this. Does that make sense? Yeah, probability density function. And then if we consider n3, it's going to look something like this. This is essentially when n is 3. Okay? So this is the probability density function, okay? So what does this tell us? For the particle sitting in the well, we can, let's say, let's just focus on when n is 1, right? The probability of finding this particle is maximum at the center, right? When we consider n equals 1. Does that make sense? And then when we are away from the center, the probability decreases, right? And then what about when n is 2? At the center, what is the probability of finding this particle? 0, right? So in this particular case, the probability of finding this small particle is 0 at the center. But it's maximum at this point and then at this point. Okay? But for n is 3, again, the probability is maximum at this point and at this point and at this point, right? So that is exactly kind of like what it tells us. And this one has kind of a very important implication because again, in quantum world, or by solving Schrödinger equation, it's gonna tell us only probability. It's not gonna tell us where the particle is going to be exactly, right? Because as you see, the probability varies, right? Like at every kind of fixed position here. Okay. So then, what about the average value of position? Okay. By solving Schrödinger equation, the average position of this particle is what? d over 2, right at the center. But let us consider, another thing. If you look at this average value, does it have n dependency? Does it depend on n? No, right? But does that make sense just by looking at probability density function? Let us look at this. When n is 1, what is the average? It turns out it's kind of symmetrical around the center point, right? So at the center, what about when n is 2? It's also symmetrical around the center. So when you take actually average of that, you can see it's going to be actually at the center. Does that make sense? And then what about when n is 3? Again, symmetrical around the center. So this is why when we get the average value here or expectation value, it is exactly at the center, and then it doesn't matter which n you are dealing with, right? Regardless of n, it's going to be symmetrical around the center point in terms of probability distribution. Does that make sense? Okay. So, again, in quantum world, it's not going to tell you the deterministic value of position. It's going to tell you only about the probability distribution, okay? And then when you're dealing with this probability distribution, how are we going to interpret that? We have to actually use a statistic, approach, basically, which require us to get average value and standard deviation, okay? So we now we got the this probability density function, and then we got the average value, and the next step is to find out standard deviation of position. Okay, standard deviation position. So just by looking at this distribution, right, probability distribution, what would you expect for standard deviation as n changes? As n increases, what would you expect for standard deviation of position? Okay, let me just ask you one more time. Okay, just let me rephrase. So, like as n increases, how the value is going to be scattered off from the center point or average value, right? That is essentially kind of what the standard deviation is, right? So if a standard deviation is large, that means it's scattered off more from the center point, right? So just by looking at this one, you can kind of tell, as we increase n, what that means is that we are going to have more bumps, right? So that means as we increase n, standard deviation is going to increase, right? Just by just looking at this one, right? And the standard deviation is going to be the smallest when n is 1, right? Does it make sense? So that is essentially kind of what we take from just kind of investigating this probability density function. And then we are going to actually work on, getting standard deviation. But like I just kind of want you to kind of be aware of like the situation here, right? I mean, like we are looking at the particle sitting in the bucket with infinitely high wall, right? And then when we are considering small object like electron, that particle is going to have wave characteristic. And then that wave characteristic can be understood by solving Schrödinger equation, okay? And then when you do that, like the physical quantity that we are interested, for example, position or momentum or energy, those can be all calculated, okay? That is essentially kind of what we have been working on. Does it make sense? Okay, so I just want you to be aware of, like the what we are really focusing on here, okay? Okay, so with that, let us now get into the standard deviation of position. Okay, this one is also kind of lengthy process. This is why so that's why I actually brought this note. Okay, because if I write, it's going to take just 1 full hour. Okay, so standard deviation of position, again, that is denoted as sigma x. So you can calculate this standard deviation either using this expression or this expression, okay? It's your choice. And by the way, we already obtained the average value or expectation value, which is this x bracket, right? X bracket we already know, okay? But this x square bracket we don't know, or like this part we don't know, so we have to evaluate that. So, like I'm gonna take just kind of square here, then sigma x square is essentially, the bracket average of this square of difference, right? So the way we do is that, since this one is a bracket here, so what we do is that we actually use the operator of this one and then put it in and then sandwich between psi and star and psi, okay? And it turns out, this x bracket is constant, so we already know, consider that as a constant, and that x, that is a position, operator of position, simply x. Okay, we already kind of know that. You just kind of plug it in here. And for integration, it has to be over the entire domain, from negative infinity to infinity. But we are again dealing with 3 different domains, right? Like the wall is located at x is 0 and x is d, right? So with that, we are essentially kind of looking at this part. This is a region 2 that we are interested. This is outside of the well. And then for these regimes, psi, as you know, is 0. So this is y, this is 0, and then this is 0. So then we are really looking at this inside the well, right? And then for that one, you just kind of expand this part, okay? So that is x squared minus 2x, x bracket here, this is average value or expectation value, plus x bracket square, okay? So in the sense, we already know x bracket, so this is essentially constant, right? d over 2, we already know that. So in the sense, if we express in each term, this is x squared, this is variable, but the x bracket is a constant, so it comes out of the integration. And then here, this x bracket square also is constant, comes out, okay? So this is essentially kind of what we get. And then we can actually simplify this one further because, like if you look at this one, what is this value? You guys remember? 1. Why? This is a probability density function, right? We are essentially integrating from 0 to d, technically negative infinity to infinity, right? So in the sense, when we sum up all the possibility or probability, it has to be 1. That's normalization condition. So this one has to be 1. And then what about this one? This is actually, by definition, X bracket, right? So when you express X bracket here, expectation value, it turns out this one, right? Psi n star X psi n. This X is just kind of a just variable, so you can just move just a little bit inside, doesn't matter. So anyway, so this is X bracket here, okay? So then we can simplify further by basically this one is a minus 2x bracket square plus x bracket square. So this one is simply minus x bracket square. But now the question here is this part, right? And then we already know psi n, that is essentially the solution for the Schrödinger equation, right? For this particular case that is given here. And then if you just kind of plug it in here, okay, that is x squared and sine squared there. Okay, and then 2 over d square root, it comes out as 2 over d because we are doing square, right? And then if you look at this one, it's kind of pain, right? By just looking at this one, you have to do integration by parts. How many times? You have to do twice, right? Because it has now x squared. Okay, so, it's a lengthy process. You have to do integration by part twice. So if you do that, okay, so this is essentially the process here, like every step, but you can just take a look and you can verify that. So here, I'm using trigonometric identity here. Sine x squared is simply 1 minus cosine 2x over 2. Okay, you just kind of replace that, and then this is becoming x squared over 2. This is first term, and the second term is going to be minus x squared over 2. Okay, x squared over 2 cosine 2n pi over dx. Okay. And then the first one, easy to integrate. So we do integration here. And then here we do have this part. Okay, and then you can actually simplify further. For example, like now 2 over d is in front. You actually bring it inside. Okay, and then you bring out this 1 over 2. So it becomes negative 1 over d. And then we have this x squared cosine 2n pi over dx, and then here you can actually do integration by parts. Okay, so for this one, like you use this one uv minus integration v du. So like this is essentially kind of the steps for integration by parts. Once you do that, okay, so here what we are really focusing on, this kind of a pink underlined equation. Okay, this expression. Okay, this part can be done using integration by parts. If you do that, it can be written as this one. Okay. So once you get this, now we have to evaluate this term at d and 0. So if you do that, if d goes inside, sine 2n pi, obviously 0, and then when 0 goes in, obviously 0, so this term goes away, and now we have this term. Okay, so then if you look at this term, x is here, and then sine is here, right? Sine x is here. So you have to do integration by parts one more time. Okay, so if you do that, this is kind of setting up integration by parts again. For this one, we can do integration by parts using these terms. And then if you do it, now this is the expression we get. Okay. So then once you get that, you have to do integration here. Okay, again. And then cosine becomes sine, and then it turns out when you put this d again inside, there's a 0, and then if 0 goes inside 0, so the whole term goes to 0. And then now you have to evaluate this one. Okay? So if you do that, if d goes inside, cosine 2m pi, that is essentially 1, right? And then 0 is going inside here, is essentially like a 1. So if you do that, it becomes this d square times d over 2n square pi square cosine 2n pi. Okay? So cosine 2n pi is 1 here. Okay? So if you do that, okay, so here, by the way, if 0 goes inside, obviously this is 1, but 0 also goes inside here. Okay? So this is why the subtraction part is essentially 0, so you only have this term surviving. Okay? So then cosine 2n pi is 1, now you have d cubed over 2n square pi square. Okay? So then what is this term, by the way? This term was essentially obtained by working on this equation only. Okay? So it's a kind of a lengthy process, but it can be done. And then now we got the value for this integration, and then if you plug it back in, okay, and then that is essentially this x square bracket. Okay, x square bracket is, look at this one, d square over 3 minus this one, 1 over d times d cubed over 2n square pi square. Okay, we just kind of plug it in here. Minus 1 over d is here. Okay, minus 1 over d, minus 1 over d, and then d cubed over 2n square pi square. So then we got this, x square bracket. Okay, now we can evaluate standard deviation. Okay, that is essentially x square bracket minus x bracket square. X square bracket, we just got it, right? From here. Yeah. So that is essentially, this part. Okay, this one comes down. Here, and the x bracket, we already know that is a d over 2, right? Minus d over 2 squared. Okay, and then you take, in order to get the standard deviation, you take the square, right? So if you do that, this is essentially what we get. Okay, standard deviation of the position. Okay, so it was a lengthy process. But here, again, let's just verify, if our understanding or, if our expectation was also matched. Okay? For example, here. So how does standard deviation change with n values? Okay? So when do we have the smallest standard deviation? N is 1, right? So here, when n is 1, okay, so if n is getting larger and larger, okay, what does it mean? This one becomes kind of smaller and smaller, right? So that's why we have, larger standard deviation, right? So in the sense, doesn't actually match with kind of our observation, right? It does, right? And then this is essentially kind of like how we can understand this wave function, or more precisely, probability density function. Okay, this is why probability density function is actually very important parameter in quantum mechanics. Okay, because it tells you, probability distribution of the position. Okay, because think about it, like when we work on dynamics, most often the parameter we are dealing with is essentially position, right? And then velocity and energy, etc., right? So, this is essentially kind of how we approach for solving Schrödinger equation. So now we actually looked at position, right? So in the sense, we looked at the expectation value of position or average value, and then we looked at standard deviation of position, okay? And then the next parameter we are gonna deal with is essentially the momentum. Okay, so expectation value of momentum. Okay, again, the momentum or velocity, because momentum is a mass times velocity, right? And then if we know the material that we are dealing with, let's say electron, if we know the mass of electron, we can easily correlate between momentum and velocity, right? And also, in quantum world, this momentum or velocity has probabilistic value. Okay, so this is why we again want to evaluate expectation value of momentum or expectation value of velocity and also standard deviation of them. Okay, so we want to find out this momentum. So let us look at this momentum, expectation value. And then, as I noted before, like the momentum operator is written as this one, okay, minus IH bar dou over dou X. Okay, so this is the, kind of the operator value. So, and then with this one, again, we are evaluating from negative infinity to infinity, okay, for the whole domain of X. And then again, we are looking at the same problem, right? So in the sense, we are essentially separating into three domains, outside of the well, and inside of the well. And outside of the well, psi is wave function is 0 anyways. That's why we are eliminating this first term and third term because it's essentially 0. Again, for the same reason. And then now we are looking at just this domain, right, inside the well, from 0 to D. So then we just simply write down, this part again with a different domain selection. And we already know this wave function, psi n, and then we plug it in, okay? So this is essentially kind of also the process or the answer to one of the questions you guys asked during the class. Okay, how do we apply this dou over dou X? Okay, so that is essentially kind of what we are gonna do here. So if you just kind of plug it in, now psi n star anyways is an all real number. This is why, like just square root 2 over d sine n pi over dx. But here, if you look at this one, this is a minus IH bar dou over dou X. This dou over dou X will be acted upon the next one. Okay, so in the sense, if we just write down square root 2 over d, but anyways, square root 2 over d is a constant, so it can come out of the derivative, and then it will be merged with the square root of 2 over d for this part, and then it will come out. Okay, and then with that, this d over dx, right, or dou over dou X, because here we only have X dependency, it becomes ordinary differential. D over dx will be upon this sine n pi over dx. Okay, so like a dou over dou X will be acting on the next one. Okay, so this is wave function. So with that, now we are taking derivative for this one. So then this whole thing will be n pi over d times cosine n pi over dx. Okay. So then, again, you can actually move this one out of integration because this is constant n pi over d. And then let's use a trigonometric identity. Sine 2a is essentially 2 times sine a cosine a. Okay, so then sine a times cosine a is sine 2a over 2. So, like we have sine a and cosine a here, right? So in the sense, we replace that with sine 2n pi over d times x over 2. Okay? So this one, it's easier to integrate. Okay, we don't have to do any integration by parts. So once you do integration for this, now it becomes negative cosine 2n pi over dx. And then here, if you kind of substitute d inside, it becomes 1, and 0 goes inside 1. 1 minus 1 is 0. That's why we get actually 0. Okay? So it turns out the average value of momentum or expectation value of momentum or velocity turns out to be what? 0. Okay. So in terms of like a kind of average value of a velocity, okay, average value of momentum, it turns out it's 0. Okay. I wanted to ask you first, but I forgot. Okay. I'm not sure if this one was kind of what you are expecting. Okay. So for example, I mean now I'm asking too late, but think about the particle sitting in a well. Okay. Here, look at this one. The particle sitting in a well. If you actually think about what is the average velocity for this particle, would you have guessed to be 0? Maybe, right? Maybe. So because like anyways, like it can have different momentum or velocity values. Okay, this is gonna have kind of probabilistic also kind of distribution, but when you get average value of that, it's going to be 0. And also if you look at this value, does it have n dependency? No. Regardless of n, right? Regardless of n, the average value of momentum or velocity is 0. Okay. So now we got this average value, and also we can obtain the standard deviation of velocity. Yes.
Is there because these waves are oscillating and then just kind of cancel each other out?
So basically, I mean, you can take any values of velocity for this particle, for example, like when we are looking at the position of that, right? Position of that, if you actually, this one, for the position, it has, different probability at different place, right? So for example, like for n is 1, the probability of finding this particle at the center point has this much value, right? And then probability of finding the particle at this point has this much value, right? But it has probability distribution, but when we take average of that, it turns out it's right at the center, right? But for momentum, it's a similar concept. The particle can take, it's kind of hard to describe within this, this probability function, because probability function only tells you about the position, right? So when we actually think about just kind of velocity, the particle can have different velocity values, but it has also probability. For example, if I draw the number, this particle can have value of velocity, let's say 1 meter per second, but the probability of that is, let's say, 1%. And then that velocity can be also negative 2 meter per second, but the chance is, let's say, 2%. When we take all the considerations, if you take average of that, it turns out the velocity is 0. So instantly, or sometimes you can take any random values of velocity. It can be positive values and it can be negative values. But when we consider all those distributions of velocity and take average of that, it turns out the velocity is going to be 0. So maybe another way to kind of express here is, maybe another simple way is think about the velocity distribution, okay, or momentum distribution, okay, and then it will be, the shape is kind of it can be different, but if I simplify, let's say it's kind of bell shaped, let's say, and then the center point is essentially what? 0. So the momentum or velocity can take any values with the probability, but when we take an average of that, or the shape will be symmetric around 0 point. Does that make sense?
kind of I suppose I'm just thinking about in terms of an electron. I wouldn't assume that the average velocity of all of those was 0 per se. You know.
So in this case, we are essentially confined, right? I mean, like the particle can only move between the walls, right? So in the sense, this particle can move to the right, can move to the left. So the velocity can be positive or negative, right? And it's gonna kind of moving, and then it has a wave characteristic. But anyways, this kind of even for wave, it has a velocity, right? The moving speed, like even though it's a speed, and it's a kind of a standing wave, it can kind of bounce back and forth, right? That is essentially kind of what the standing wave is. So in the sense, if we take the average of that, it's essentially kind of 0. So it's essentially kind of it's not really stationary. It's still like a particle moving around, but it can take various velocity values, right? It can take positive values and negative values, right? Kind of moving this way and then this way.
But just because we've confined it, that confinement isn't moving, and so the average of all the possibilities would be 0.
That's essentially how you can take to, yes. So here, and then this is the kind of average value of the velocity or momentum, and then also we can evaluate, how far this distribution is, right? Like how the shape is kind of, basically scattered or the centered around or close packed around the center, okay? So for that one, we need to evaluate standard deviation, right? So in the sense, we are gonna look into this standard deviation of momentum, okay? So it's the same idea, okay? It's just like instead of position, we are essentially considering momentum here. So in the sense, here again, we are looking at this, the definition. This standard deviation of momentum square is essentially p square bracket minus this p bracket square, okay? But we already know what this p bracket is, right? This is essentially expectation value of momentum, which is 0. So, this one we already know, but now we have to evaluate this p square, okay? So for that one, we know what this, because p square is essentially what? This one is essentially p times p, right? And then we know the operator for p, right? That is essentially negative IH bar dou over dou x. And then, there are 2p. So you are essentially kind of writing twice here. And then, since there is a bracket here, what that means is you sandwich between psi n star and psi, and then integrate over the entire domain in X. Okay. So, if you do it, you will obtain the result. Okay. So, but this one, is again, you can try. This is actually a homework problem. Okay. As you know, this is the homework 2 has been assigned. Okay. You can actually work on this on your own, and if you evaluate this one. Now sigma p, it turns out it is actually m pi h bar over d. Okay? So then, if you look at this standard deviation of momentum, now it has n dependency, right? So what does it mean? Just by looking at this one, as n increases, right? If we are considering the wave function with higher n, standard deviation increases. So what that means is that, in terms of this distribution again, p, if we increase n, it will be, a wider and wider distribution. Does it make sense? Okay. If you have a kind of larger n, the velocity value will be scattered more off from the center. Okay. All right. Okay. So then, we essentially evaluated the position and momentum distribution, right? I mean, for that one, we kind of obtained the expectation value and standard deviation, okay, for, a position and the velocity each. And now we are gonna actually apply kind of a Heisenberg uncertainty principle. Okay, here. Okay, as we stated before, the standard deviation of position multiplied by standard deviation of momentum must be equal or larger than h bar over 2. Okay? So we already obtained the sigma x and sigma p, right? And then for this particular case, infinite potential well, sigma x was d square root 1 over 12 minus 1 over 2n square pi square. Okay, so sigma x, what I'm doing is that I'm actually just copying this one value. Okay, sigma x here, we already obtained this value. And then sigma p, we already obtained from here. Okay, with that is essentially n pi h bar over d. Okay, so again, this one is just infinite potential well. Okay, if you are dealing with the different shapes of potential, this value will be different. Okay, but for this particular infinite potential well, the standard deviation of position, standard deviation of momentum is given like that. And then once you evaluate that, it turns out that is n square pi square over 12 minus 1 over 2. Okay? So it has, the n dependency. So let us kind of look at the different n values. Okay? For n equals 1, if you evaluate that, that is h bar over 2, 1.14. And then when n is 2, the value is h bar over 2, 3.34. And so on. Okay? So actually, as you increase n, the value is going to increase. The minimum value that you can obtain is essentially when n is 1. Okay? When n is 1, h bar over 2 times 1 times 1, 4. So look at this one. Heisenberg uncertainty principle still holds, right? So even when n is the smallest, okay, is still larger than h bar over 2. Okay? So what does it mean? For this infinite potential well case, if you really try to confine sigma x, sigma p is gonna increase, right? So again, in this particular case, it actually tells us that, for this particular case, right? When particle is sitting inside infinite potential well, you cannot quantify position and momentum simultaneously. So if you try to find the position of this particle, the momentum value, you are actually less uncertain about that. Does that make sense? The same thing. If you try to find out the velocity of this particle, you are gonna, know the position with a much less accuracy. Okay, so it's kind of counterintuitive, right? I mean, like bulk scale, we can exactly quantify position and velocity very precisely. I mean, that is the whole purpose, right, in classical mechanics. But in quantum world, if you know position, you're not gonna know velocity. And if you know the position, or if you try to find out velocity very accurately, position you have to give up. Okay, so that is essentially kind of consequence. Okay. Okay, so with that, up to this point, basically, we actually finished here infinite potential well. And then we are going to consider other cases. Okay, so we are going to consider other cases. that is essentially, like, what if the wall height is not infinity? Okay, so like for now we consider very simple case where the wall height is infinity, but like we are gonna actually reduce the wall height to finite value, and then we are gonna see how the particle behaves or how the wave behaves. Okay, so for that one, like I mean, before we actually dig in, I want to kind of discuss one important theorem. Okay, this is going to be kind of basis for tackling the finite potential well. So let me just kind of discuss this briefly. So here, this theorem states that if the potential u of x, this is essentially the constraint, right? Constraint. This potential is an even function of x. This psi of x, the wave function or the solution for Schrödinger equation can always be taken to be either even or odd function. Okay. So, like for those who forgot what even function and odd functions are, these are essential definition. Okay. So even function, like if you can describe like this way, is all even function. Okay, so for example, f of minus x equals fx is kind of like a symmetrical around the, or like, I mean, the mirror image around this vertical line, okay, at x0, that is essentially, the even function. So that is essentially kind of cosine function, right? I mean, when you kind of cosine, it's essentially mirrored around the center plane, that is essentially even function. And the odd function, like if you can describe function like this, is all odd function. Okay, so f of minus x equals minus f of x. Okay, so in this sense, kind of sine function, right? It's kind of a, like the symmetrical around the origin. Okay, then it's essentially odd function, right? Sine is like that. So that is the definition of even and odd function. Okay, and for that, we can actually use the Schrödinger equation and kind of prove that. But for this one, I guess we can start working on tomorrow. Okay, so we can end today's class here.